Finishing up with our basic introduction to the nervous system, we looked at neurons, we looked at the overall organization of the nervous system, we looked at glial cells. Let's look at some of the other properties and some important other features. So, as we covered back when we did the muscles, remember all action potentials are the same size. No action potential is bigger. That would be one of the reasonable ways when you're thinking about the force of muscle contraction. You might think, oh, in order to make a muscle generate more force, we'll use a bigger action potential. Remember, that didn't work. All action potentials are the same size. Instead, for an individual muscle fiber, we had to increase the number of action potentials per second, and for the entire muscle, we had to use bigger motor units, and we had to recruit more motor units. Well, so all action potentials are the same size, but not all action potentials travel at the same speed. So let's look at the speed of impulse propagation. Propagation is not related to stimulus strength. That might be another thing that you would suggest. You would suspect. If somebody just gives you a little light tap and you feel that, maybe that's that you got. That would make a slow action potential, where if somebody punched you really hard, that would make a fast action potential. No, that's not the case. It doesn't have anything to do with the strength of the stimulus. Instead, it has to do with the diameter. So larger fibers, larger in diameter, conduct impulses faster due to their size. There's less resistance. Think of it this way. Think of these axons as like big pipes. If it's a big wide pipe, then it's easier for water to flow through. It's a very narrow pipe, it's harder for water to flow through. So that's why large diameter axons carry faster impulses than narrow diameter. Also, myelinated fibers conduct impulses faster due to what's called saltatory conduction, and we'll look at that coming up. So these are the two things that determine then the speed of the action potential. Number one, the diameter of the axon. Number two, whether or not it's myelinated. Myelinated are faster, non-myelinated are slower. So we can categorize axons in your body by their size. The largest we call A fibers. A fibers, you can see in the diagram there, they show A alpha, A beta, A delta. Unfortunately, they don't show B, which is next, but you can still see the relative changes in diameter. So A are the biggest in diameter, and they are the fastest, all right? So they carry action potentials at the rate of about 120 meters per second. Now, what do you know, in your experience, it's about 120 meters long? Yeah, you have no idea what a meter is, do you? A meter is roughly a yard. So what can you think of that's maybe roughly 120 yards long? Yeah, a football field or a soccer field. So the fastest axons in your body can carry a nerve impulse, an action potential, at a speed of roughly 1 football field per second. That's pretty good. That's faster than the fastest cornerbacks in the NFL. Man, if you had a receiver that could run 1 football field per second, you would score touchdown after touchdown after touchdown. Of course, there aren't any of those either, are there? So which fibers are this? These are myelinated somatic. So remember the somatic nervous system? So these are somatic, sensory, and motor. So remember, somatic sensory are your skin senses. Somatic motor are your skeletal muscles. And doesn't it make sense here that the fastest axons in your body would be going from your skin senses, coming to the central nervous system, and then going from the CNS out to your skeletal muscles? If somebody throws a knife at your head, you need to duck right now. So you want some really fast action potentials making it out to those skeletal muscles so you can move in time. And if your hand is on fire, you need to know about that right away. So it makes sense that your skin senses have really fast axons to let you know what's going on. Then next come B fibers, which are the medium size. They carry action potentials at a speed of around 15 meters per second. And 15 meters per second, or 15 meters, what do you know that's about 15 meters? I'm guessing like at your house, maybe your living room is maybe 15 meters. At Pima, the classrooms were on the order of maybe 15 meters, the room, that's how wide it was. So think like one living room or one classroom per second. All right, that's still pretty darn fast. So these are myelinated visceral axons. These are autonomic preganglionic. Now we don't really know preganglionic yet. We'll come to that later. But for just right now, think of it's autonomic fibers that are the B fibers. So in other words, pains and signals going to and from your liver are not quite as crucial in terms of speed as, knives coming at your head or somebody setting your hand on fire. The inside of our body, we're going to have it with us for quite some time. So if it takes a little slower to get there, that's okay. And then finally, the smallest fibers, C fibers, they carry impulses at only around 2 meters per second. Now, what's around 2 meters? Can you think of anything that's 2 meters? It was so great, I had a guy in my classroom one semester who was 6'6", and that's just about exactly 2 meters. So I said, Emmanuel, stand up. And everybody got to see 2 meters. So, and then we pointed out that Emmanuel, if you were to pinch Emmanuel's big toe, it would take like a second for that impulse to get to his brain. All right, there's a disadvantage of being tall, okay? So these are non-myelinated, and you might think non-myelinated, why would you want to have things non-myelinated? Well, myelination makes the whole axon thicker. And so if all the axons in our body were myelinated, we would look like the Pillsbury Doughboy. We would look like the Michelin Tire Man. We would be all puffed out. So your body kind of saves myelin for the really important pathways, and it doesn't myelinate the less important pathways, all right? So these are some somatic, sensory, and all autonomic postganglionic. Again, we don't really know what those terms mean yet, but we'll see. For example, you have two kinds of pain pathways in your body. One kind of pain pathway for the emergency type of pain, like when somebody sets your hand on fire, those are A fibers. But like the pain of a sprained ankle the day after you do it, just that kind of dull, throbbing pain, that's not really crucial, is it? Your body's just trying to remind you, hey, your ankle's hurt, it's healing, don't walk on it. So some pain signals are not nearly as important. So those are the C fiber pain, the slow pain signals in your body, okay? Here you can see a chart. These are for frog axons, but here they actually show the B fibers. So you have A alpha, A beta, A delta, B, and then C. And you can see the relative speed of transmission. Just note that the bigger the fiber, the faster. So the fatter the fiber, the faster it flies. The fatter the fiber, the faster it flies. So big axons, big wide axons, fast. Small narrow axons, slow. Okay? Let's then take a look at this thing called saltatory conduction. We're going to contrast continuous conduction, which is what happens on non-myelinated axons, with saltatory conduction. So continuous conduction means we have a step-by-step depolarization of each portion of the length of the axal lemma. So that means that the action potential has to depolarize every single little bit of the axal lemma, of the axon membrane. In contrast, in saltatory conduction, these are on myelinated axons again, what happens is depolarization occurs only at the nodes of where there's a high density of ion channels. So what happens here is that if you've ever studied any electricity and you've studied what a capacitor is a way of keeping charges, of isolating them and then having them jump across from one side of the capacitor to the other. So that's what happens here. On a myelinated axon, instead of the action potential regenerating itself at each little point along the axonal membrane, it only has to regenerate itself at the nodes of so it can literally leap down the axon, and that means it goes much, much faster. So take a look here. Here's an example. So look on the left, we have continuous conduction, that's on a non-myelinated axon. Then look on the right, we have saltatory conduction on a myelinated axon, okay? So look at on the left. You see after 1 millisecond, the action potential has moved a little ways. After 5 milliseconds, it's moved a little further. After 10 milliseconds, now it's a little further still. But look at corresponding on the right-hand side. Look at what happens on a myelinated axon. After 1 millisecond, there's not all that much difference. By the time we get to 5, look, on the myelinated axon, it's already been able to jump over 1 myelin sheath, so it's already a little further. And look, by the time we get to 10 milliseconds, it's been able to leap over all those myelin sheaths, and it's now way, way down the axon. Whereas on the left, look at the continuous conduction is still on the first half of the axon. So that's saltatory conduction. Now, by the way, you might think saltatory conduction, that's because of salt, because, remember the ion channels on the axon, or sodium and potassium channels? Well, that would be a reasonable thing to think, but that's not true. It turns out that it comes from the Latin verb saltare, which means to leap. So in this case, the action potential is leaping over the myelin sheaths from one node to the next. So that's why it's called saltatory, because it's leaping, okay? Saltarello, by the way, was a dance of the Middle Ages. If you're into Middle Age music and Renaissance music, you probably already knew that. Here we see people dancing the Saltarello, or a Saltarello. Look at who the composer was. Vincenzo Galilei. Anybody heard of him? Maybe you've heard of his famous son. His famous son was Galileo Galilei. There you go, one of the greatest physicists of all time. So, see, and here his father was basically just a drunk who played the lute in bars. So, see, no matter where you come from, you can still be world famous and famous to all of history, okay? So, by the way, I can play that on my guitar. Sometimes when we do it in the classroom, I bring in my guitar at the end of the semester and we play that. So you can see, if you can read sheet music, on the left goes do 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 doom do do doom 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 do do doom doom do do little little doom do do little 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 doom do dum 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 da dum 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 da dum 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 da dum dum. All right, I'll stop. Thank you. So let's talk about another important concept here: white matter versus gray matter. So, gray matter consists of cell bodies, unmyelinated axons, dendrites, and glial cells, whereas white matter is myelinated axons. So think of it this way: white matter is basically like the wiring, all right? And you can see it both in the spinal cord and in the brain. Wherever you see white matter, of course, did they make it white and gray on this diagram? No. They made it kind of, I don't know what, like dog puke, I don't know what. But the lighter is supposed to be white matter, and the darker is supposed to be gray matter. So wherever you see the light matter, you're basically seeing insulated wires. Those are myelinated axons. So that's the wiring. Those are the pathways. Wherever you see the dark matter, those are the actual cell bodies, plus some glial cells, plus some unmyelinated axons. So notice in the brain, the cell bodies are all around the outside edges of the brain, and the wiring is all in the middle, all right? So white matter and gray matter, all right? Let's then start to look overall at how neural transmission works, okay? So as we mentioned before, neurons take input in through their dendrites, for the most part. And what happens is neurotransmitters bind to receptors on the postsynaptic neuron, and that often opens ion channels. So in the bottom half of the illustration, well, you can see it in the top a little bit as well. So you have these synaptic vesicles, which are little bubbles, those little green bubbles on the bottom. They're full of neurotransmitter. They're releasing the neurotransmitter. It's diffusing across the synaptic cleft, just like we saw in the neuromuscular junction, and then binding to those receptors, okay? And the receptors are often ion channels. So when the neurotransmitter binds to the receptor, it opens the ion channel. And then what happens is the flow of ions causes electrical current. Remember at the NMJ, that was the muscle action potential. In general, from now on, when this happens on neurons, we're going to call those graded potentials. We call them graded because they can vary in size. Whereas the action potential is always exactly the same size, graded potentials can vary in their size, all right? And what's going to happen here is that the graded potentials, so if you look in the top half of the illustration, the graded potentials are going to flow down the dendrites, and they're all going to converge in the axon hillock. Remember we said the axon hillock is where we make a decision, where the neuron makes a decision, all right? Oops, I talked over the transition, not supposed to do that. So when the graded potentials arrive in the axon hillock, they may push the membrane of the postsynaptic neuron to threshold. So what happens is, remember, the axon hillock, also we can call it the trigger zone, is where the neuron decides whether or not it's going to fire an action potential. And what happens is the graded potentials all add up. And if they add up to a certain amount, which is called the threshold, then that triggers the action potential. Think of it as like if you're filling the bathtub with water, eventually the water will get to the top of the tub and then it'll start flowing over the edges and you'll flood your bathroom. That would be like the threshold. The top of the tub is the threshold. Once the water makes it over the threshold, it's going to flood the bathroom. But once the graded potentials add up and go over the threshold, that's what causes the neuron to fire an action potential. So threshold is achieved, then the postsynaptic neuron fires the action potential. The action potential then propagates down the postsynaptic neuron, causing the release of neurotransmitters at the end of that neuron. So see, the whole cycle continues over and over again. If the graded potentials hit threshold, then the neuron fires an action potential. Action potential propagates all the way down the axon. Then it's going to cause the release of its own neurotransmitters. Those will bind to receptors on another axon, on another neuron, on the dendrites rather, and that may cause it to reach threshold, and then you get the whole thing continues again. Then it will fire an action potential. Okay? So which of the following statements is false? Ascending pathways are sensory. Continuous conduction takes place on myelinated axons. Nerve impulses travel faster on fibers with larger diameters. The ANS is part of the PNS, or astrocytes provide structural support and assist in forming the blood-brain barrier. This kind of ties together everything we've done so far in this basic neuro PowerPoint. This is forcing you to go back and think about all the things we talked about. So 4 of those are true, 1 of those is wrong. Which one is wrong? Yeah, continuous conduction is on non-myelinated axons. Saltatory is on myelinated. Ascending pathways are sensory, remember? Those are the afferent, ascending are afferent, whereas the descending are motor, those are efferent. Nerve impulses definitely travel faster on fibers with larger diameters. Remember, the fatter the fiber, the faster it flies. The ANS is part of the PNS, along with the SNS. And astrocytes do help to provide the structural support, and they assist in forming the tight endothelial junctions in the capillaries that form the blood-brain barrier.